This is our third example. We have these two folks, Brooke, who is walking west along a path, and we have Jamel, who is walking, Jamel's walking west, Brooke is walking east. We have these parallel paths. They're 15 meters apart, and you can see the rates. Brooke is jogging at 3 meters per second. Jamel is walking at 1.5 meters per second. And this vertical line here is the time zero line. When the question is, when it's 10 seconds later, how fast is the distance between them changing? So the question here is, what geometric formula ties all these together? And one big mistake would be to start thinking about a bunch of triangles like this and trying to do some crazy geometry with trig functions. And it turns out, let's look at this relationship, but it turns out a pretty simple situation will work. And you can see it with this red triangle. Let me animate this for you. So notice what we have going on. We have Jamel's westward motion, but it's in the it's in the horizontal. It's all horizontal motion, right, in the direction of the x-axis. And Brooke too, she's moving east, and her motion is all parallel to the x-axis. So they're both parallel to the x-axis. So I want you to kind of think about what's happening to this base, right? The base of this triangle. We have the Jamel portion, right, from on the left side of the time zero line, and we have the Brooke portion on the right side of the time zero line. But the base of this triangle is just the two components. So we're going to name these components. So where Jamel is, it's written as J here, but since it's in the x-axis direction, when we get to the problem, we're going to call this point x sub j, or we're going to refer to the distance between where Jamel is and time zero. We're going to measure that distance as x sub j. And same thing, here it's marked as b, but we'll call this distance between Brooke and the time zero line, we'll call that x sub b. So what's the scenario? Well, if we think of just the total base of this triangle as the distance we're working with, and we call that x, right? We're going to have the sum of the Jamel component plus the Brooke component. That's going to be our x component. Well, then we just have the Pythagorean theorem. So this doesn't look exactly like the last problem. It has a couple of nuances. And as I said, we are going to call the distance that Brooke has traveled x sub b. So the rate at which Brooke travels is the differential, dx sub b over dt. And similarly for Jamel, his distance traveled is x sub j, so the rate of change is dx sub j over dt. We have the same derivative, the same implicit derivative as before. And then here, make the note that you see that we've added the two distances that Jamel and Brooke have traveled together. And I apologize, there's a slight mistake here. This should be a B instead of a J. That subscript should be a B. And so here's the timestamp in the problem, 10 seconds later. So let's start calculating distances. And the first thing I want you to note is that y is fixed. It doesn't change at all, so dy dt is going to be 0. That's going to be important. All right, next we have, like we said, x sub j and x sub b. And then these are their rates. That's dx sub j over dt. This is dx sub b over dt. And then these are the total distances. This is x sub j and x sub b, the distances that they walked in those minutes. And the sum of 15 and 30 is this 45. That's going to be the total distance. And then we're also going to add the differentials. Right, we're going to add 3 meters per second with 1.5 meters per second to get the rate at which overall the x variable is changing. So when we plug all of these things in, and note that we have the 0 rate here, so that second term will go away. And we only have two things that we don't know: the distance between them, which we can calculate using the Pythagorean theorem, and the rate at which that distance is changing. So we are just plugging the 47.3 in for the s and dividing through on both sides by the 47.43 meters. And notice that the meters cancel, and my units are correct. Like we said in when we were looking at the earlier problem, taking care of our rates is important. It's also important to understand that that's why one reason we knew it was legitimate to add those two rates. They were headed in the same direction, but they also had the same units. We can't add or subtract two differentials if they don't have the same units. We can't always add or subtract them just because they have the same units, but it certainly wouldn't be okay to add two things that had different units. So that was a hint. Just to wrap this up, I want to talk about the process we use. I think it's really important to sketch this figure. Now, I've been doing it for you digitally and showing you, but that's a big part of the problem solving, because the whole point is to get this geometric formula that relates all the givens and unknowns, and then we differentiate it implicitly. That's going to be our rates formula. So also the timestamp will be important. The timestamp allows us to calculate distances and heights, the depth of fluid in a tank, the angles, the volume or surface area. So that's an important piece. Using all of that information, then we're going to plug values into the rates formula and solve for the unknown. That's the overview. Thanks for watching.